Welcome to our deep dive. Today, we're going to be tackling
Oh, yeah,
a
what?
really
Big one.
big one. Yeah, really fascinating one, and I'm so glad you're here to help us sort of wade through this.
Happy to be here.
Yeah, we're going to be looking at quantum mechanics, specifically decoherence,
Yes?
and we're going to be using this paper
Mm-hmm.
by Woji H. Zurich, Decoherence, and the transition from quantum to classical revisited.
It's a good one.
Yeah, it's a fascinating paper, and it really gets at this.
It's a classic.
It is a classic, yes.
For a reason.
Yeah, so how would you sort of explain what decoherence is in very, like, layman's terms? Because this is one of those things that I think people hear a lot but don't really understand.
Yeah, so I think the best way to think about decoherence is that it's the thing that explains how quantum systems that can be in multiple states at once,
Yeah.
right? This is super that goes away, and they start behaving classically.
Right, so we don't see our coffee cup
Right.
suddenly be in two places at once?
Yep.
It's because of decoherence?
Right. And so the idea is that macroscopic systems that we deal with in everyday life, they're never actually isolated.
Yeah.
They're always interacting with their environment,
Yeah.
even in very subtle ways. And this interaction is what causes the quantumness to kind of leak out into the environment.
Yeah.
And then we're left with just one outcome that we observe.
Oh, so it's like the environment is sort of measuring the quantum system.
That's a good way to think about it. Yeah,
even if we're not there.
exactly. Yeah.
With our, lab coats.
Yeah, it's not a conscious observer. It's really just the environment itself interacting with the system.
So what would be like a good analogy to help people picture what's going on here?
Okay, so imagine you drop a drop of ink into a glass of water, right? What happens is the ink spreads out, it kind of dissipates, and you can't really get it back together again.
Right.
It's sort of mixed in.
It's diluted into the water.
Right, exactly. And that's kind of what happens with quantum information in decoherence. It spreads out into the environment, it gets mixed in, and becomes very difficult, if not impossible, to retrieve.
So the information about the quantum system is like the ink,
Yeah,
and the environment is the water.
that's a good way to think about it.
Okay, I like that.
But keep in mind, it's just an analogy. The actual process of decoherence is a bit more complex and dynamic.
Sure, of course. But it's helpful to have these images.
Definitely.
So is it like the environment is measuring the quantum system, like we were saying before?
Yeah, you can think of it that way. Each interaction with the environment is kind of like a little measurement that nudges the system a little bit closer to classical behavior.
And all these little nudges add up.
Right. And eventually the superposition breaks down, and we're left with just one outcome, the one that's most compatible with the interactions with the environment.
Okay, so this is starting to make sense to me, but what about this idea that macroscopic objects, like, things we can see and touch, don't seem to exhibit quantum behavior?
Right. Well, that's one of the key points that Zurich makes in his paper. For those systems, decoherence happens incredibly fast, much faster than any other processes that we're familiar with.
So it's like it's happening so fast that we don't even notice.
Exactly. He gives this example of like a dust grain at room temperature, and he calculates that decoherence happens almost instantaneously, like way faster than the blink of an eye.
Wow, so that's why we don't see our coffee cups,
Right.
like teleporting across the room or something?
Exactly. The environment has already kind of collapsed those superpositions before we even have a chance to observe them.
So that's why the world seems so solid and predictable.
Exactly. It's this incredibly rapid decoherence that gives us this illusion of classicality.
Illusion, huh?
In a way, yes. I mean, the underlying reality is still quantum, but we just don't perceive it that way because of decoherence.
Okay, so this is all starting to click, but what about microscopic systems like electrons? Those things still exhibit quantum behavior.
That's right. And that's because the speed of decoherence really depends on the size of the system, the temperature, and how strongly it interacts with its environment.
So for tiny particles like electrons,
Right. They interact much more weakly with the environment.
you're kind of less susceptible.
Exactly. So their quantum properties can persist for a much longer time.
So it's not like there's this hard line
Right.
between quantum and classical.
It's more like a gradient.
Yeah.
And decoherence is this process that's constantly pushing things towards the classical end of the spectrum, but the speed at which it happens really varies.
I see. So it's like this tug of war between the quantum world and the classical world, and decoherence is kind of the referee deciding who wins.
That's a great way to put it. And Zurich dives deep into how this works, introducing this concept of pointer states.
Ah, pointer states. I've heard of those, but they always sounded kind of mysterious.
Yeah, they're basically the states that are most robust to decoherence.
So they're the ones that survive this interaction with the environment.
Exactly. And they're the ones that we end up observing as classical properties like position, momentum, energy.
So it's like the environment is this giant sieve and it's filtering out all the quantum states that are too fragile to survive.
That's a good analogy.
And the ones that make it through are the pointer states, the building blocks of our classical reality.
Exactly. And this is crucial for understanding how we perceive the world. These pointer states, they've been selected by the environment. They're the ones that correspond to the classical properties that we observe.
Wow, so it's like our reality is shaped by this constant interaction with the environment.
That's right. It's not just a passive backdrop, it's an active participant in shaping the world as we know it.
This is all so fascinating, and I have a feeling it's just the tip of the iceberg.
Oh, absolutely. We've only just scratched the surface.
We still need to explore how this all connects to information, the arrow of time, and even consciousness.
That's right. We've got a lot more to uncover.
Well, I can't wait to dive in and explore further. So let's take a quick break, and then we'll come back and tackle these even bigger questions.
Sounds good.
Okay.
Looking forward to it.
So we're back and ready to go even deeper into decoherence. I'm really fascinated by this idea that information plays a key role in shaping reality.
It's a pretty revolutionary idea, you know? Yeah, it is.
For a long time, information was considered like a passive thing in physics. Like it was just a record of what was happening.
Right, just data.
Yeah. But Zurich is saying that it's much more than that.
So, information is not just something we write in a notebook or store on a computer.
Right. It's like an active player in the universe.
Wow, okay.
Yeah, and this is where quantum mechanics gets really weird because you see, acquiring information about a system always involves disturbing it.
Right, it's like the Heisenberg uncertainty principle. You can't know both the position and momentum of a particle with perfect accuracy.
Exactly. It's like trying to observe something without affecting it, which is impossible at the quantum level.
It's like if you try to look at a tiny little butterfly too closely, you might knock it off its flight path or something.
Right. The very act of observing changes the thing you're trying to observe.
And this ties back to decoherence, right?
Exactly.
With the environment constantly measuring the quantum system. Yeah, it's like every interaction with the environment is a little bit of information being exchanged, a little measurement being made.
Like those ripples spreading out in the pond.
Exactly. And as that information spreads out, it becomes harder and harder to retrieve.
So the universe is becoming less predictable from a quantum perspective.
Right. You could say that the environment is kind of scrambling the quantum information, making it less and less accessible.
And this loss of information is irreversible, right?
That's the key point. It's irreversible. And that's where the arrow of time comes in.
Oh boy, the arrow of time. This is where I always get a little lost.
Yeah, it's a tricky concept,
Yeah.
but it's central to how we understand the universe. So basically, the laws of physics don't really distinguish between past and future.
Right. They work the same way forwards and backwards.
Exactly.
Hmm.
But our experience is that time flows in one direction.
From past to future.
Right, so why is that?
Yeah, good question.
Well, Zurich argues that it's because of this irreversible loss of information during decoherence.
Okay, so as the environment interacts with the quantum system,
Right, information spreads out and gets lost.
and this is like increasing the entropy of the universe.
Exactly. Entropy is a measure of disorder. And as information gets dispersed, things become more disordered.
Okay, so decoherence is increasing entropy, which is giving time its direction.
That's the idea. It's like you can't unspill milk or unbreak an egg because the information needed to reverse those processes has been lost.
Wow, so decoherence is not just affecting how we perceive reality, it's actually shaping our experience of time itself.
That's pretty mind-blowing, isn't it?
It is, but it also makes me think about quantum computers.
Yes.
If decoherence is constantly pushing things towards classical behavior, how can we ever hope to build a quantum computer?
Right. That's the big challenge.
Because quantum computers rely on these delicate superpositions and entanglements.
Exactly. And those are super fragile, extremely susceptible to decoherence.
So it's like trying to balance a pencil on its tip.
Mm-hmm.
The slightest disturbance will knock it over.
And that's why researchers are working so hard to find ways to protect quantum computers from decoherence.
So it's like building a shield around them.
Yeah, they're trying to create incredibly isolated environments to slow down the interaction with the outside world.
It's like putting that pencil in a vacuum chamber.
Exactly, or cooling it down to extremely low temperatures.
Right, to minimize those thermal vibrations.
But it's a constant battle.
Yeah.
Decoherence is always lurking, waiting to destroy those delicate quantum states.
But there's another piece of the puzzle here, right?
What's that?
Entanglement. This spooky action at a distance where two particles are linked even if they're miles apart.
Ah, yes. Entanglement It's essential for many quantum computing algorithms, but it's also super vulnerable to decoherence.
So if those entangled particles interact with the environment,
Their connection can be broken.
just
Yep.
like trying to have a private conversation in a noisy room.
Right. Any little disturbance can disrupt the communication.
So understanding decoherence is crucial for building quantum computers.
Absolutely.
Oh,
It's not just a theoretical curiosity.
yeah.
It has very real practical implications for one of the most exciting technologies on the horizon.
It's really amazing how this one concept connects so many different ideas, from the nature of reality to the arrow of time to the future of computing.
And we haven't even touched on the philosophical implications yet.
Oh, right. We still need to explore what decoherence tells us about consciousness and the meaning of existence itself.
That's next.
Well, I can't wait to dive into that, so let's keep going. Okay, so we've talked about how decoherence bridges the gap between the quantum and the classical worlds, how it shapes our experience of time, and even the challenges it poses for building quantum computers. But now I want to get into the really big questions. What does all of this mean for us?
Yeah, I think this is where things get really interesting because decoherence isn't just some esoteric concept in physics.
Right.
It has these profound philosophical implications.
It's really making me rethink my whole understanding of reality.
It should, yeah, because it challenges some of our most basic assumptions about the world.
It's like we've been looking at the universe with classical glasses on, and now decoherence is giving us these quantum glasses.
Exactly, and suddenly we can see all this new stuff that was always there, but hidden from view.
So what are some of these philosophical implications that you mentioned?
Well, one of the biggest ones is that it blurs the line between the subjective and the objective.
Okay, so explain that to me.
So for centuries, science has strived for this purely objective description of reality.
Right, like the universe just exists,
Exactly, independent of us.
whether we're here to observe it or not.
Yeah, like the universe is this giant clock ticking away, regardless of whether we're looking at it.
But quantum mechanics, and specifically decoherence, suggests that that might not be the whole story.
Right, it's like saying that by observing the clock, we're actually influencing its ticking.
Oh, wow. So it's not just a passive observation.
No, it's an active participation.
And this is where those pointer states come in, right?
Yeah, exactly. They're not just sitting there waiting to be discovered.
So they're not predetermined.
They emerge through this interaction with the environment.
So our reality is not fixed.
It's more like a co-creation, a collaboration between us and the universe.
That's a pretty wild thought.
It is, and it has some pretty big implications for how we think about ourselves and our place in the world.
So what about consciousness? Does decoherence have anything to say about that?
Yeah, Zurich argues that it plays a key role in shaping our conscious experience.
Hold on, you're saying that what's happening at the quantum level is somehow affecting our thoughts and feelings.
Well, remember, our brains are macroscopic systems.
Right.
And they're constantly interacting with the environment.
So any quantum weirdness that might be going on in there.
Gets quickly squashed by decoherence.
So instead of our brains being these quantum computers with thoughts existing in superpositions,
We experience a more classical defined mental state.
because the environment is constantly measuring our brains.
Yeah, you could say that.
Wow. So it's like the environment is a co-author of our consciousness.
Shaping the narrative of our thoughts and perceptions.
And that raises a really interesting question. Could consciousness be more fundamental than we thought?
You mean like not just limited to biological systems?
Yeah, exactly.
Yeah.
Could it arise in any system that interacts with its environment in the right way?
It's a fascinating idea, and it's one that Zurich explores in his work.
So we're talking about a potential link between the physical universe and our subjective experience of it.
Yeah, decoherence might be the bridge between matter and mind.
This is all pretty mind-blowing, but I have one more question.
Okay, shoot.
What about the stuff that doesn't survive decoherence?
Like those quantum superpositions that get quickly destroyed by the environment?
Yeah, are those things less real than the pointer states that define our classical reality?
It's not that they're less real, they're just less robust.
Okay, I see. So they haven't been selected by the environment.
Right. They haven't achieved the same level of objectivity as the pointer states.
So it's like our reality is a carefully curated selection of the most stable aspects of the quantum universe.
Yeah, you could say that.
And that makes me wonder, could there be other realities out there?
Other sets of pointer states that are just as real, but inaccessible to us.
It's like imagining the universe as this giant library full of books written in different languages.
And we can only read the ones in the language our brains understand.
The language of classical reality.
Right. But that doesn't mean those other books Those other realities don't exist.
Wow, that's an amazing thought.
And Zurich's work is really pushing us to think about these
You
possibilities
expand our understanding of what's possible.
and what it means to exist in a quantum universe.
This has been such an incredible journey. We've gone from the subatomic world to the meaning of reality itself.
And it all comes back to this one concept, decoherence.
A huge thank you to our expert for guiding us through this.
It's been my pleasure.
And to our listeners, we hope you've enjoyed this deep dive as much as we have. We'll leave you with this thought: the universe is far stranger and more wondrous than we can possibly imagine, and the quest to understand it is an ongoing adventure. Thanks for joining us.